Well, good evening, guys. This is going to be a pre-recorded class. And we are going to start talking basically about time series, okay? This is a class that you need to review by yourselves. And we're going to do a summary during our next class, okay? So we're going to start with time series, and I will say univariate time series first. And I will provide you with a couple of insights, a couple of things that we need to know, as well as some of the models that we're going to be using during this first part of time series. Okay? One of the main assumptions, guys, in time series is what is called stationarity. Okay? And we're going to distinguish between two stationarities, one that is a strict stationarity and weak stationarity. So let's start talking about strict stationarity first. Okay, so what is a strict stationarity? The definition is the following, guys. Now, what we are going to have is a time series of a variable, yt, okay? And t is basically going to be changing in time. So we'll have 1 up to t. So I have t observations in my time series. So imagine this one as a vector, okay? And what we are going to say is that basically that for any k that belongs to the integral space, okay, for any k and c, what we are going to define, guys, is we're going to define the CDFs, okay? And we're going to see the following. So we say that the cumulative distribution function of, let's say, y1, y2, yt, okay? And what we are going to be doing, guys, is we're going to be evaluating y at time 1, y at time 2, y at time 3, etc. Right? And what this strict stationarity requires, guys, is that this one here must be exactly the same as a CDF of y1, y2, yt. The only thing is that we are going to shift the times. Y evaluated at time 1 plus k. So this is this k here, any integral. At time y evaluated at time 2 plus k, etc. Right? So what this strict stationarity implies, guys, is that all the moments, okay, all the moments of distributions are exactly the same. So the moments, I mean the mean, the variance, skewness, kurtosis, etc. Okay, etc. So all of them must be exactly the same. So, and this assumption is very, very hard to satisfy in real life, because having just translating the distribution k periods ahead or before and having the exact distribution is very hard. Got it? So basically what we're trying to do is trying to find if we have a series like this, for example, okay, that looks very similar to a time series of prices or returns, or prices basically in the stock markets. And then so the basic idea is that imagine if you have, just take a couple of intervals in time, okay? The same size. And let's assume another interval in here, okay? This is exactly the same size as this one here. Now, obviously, guys, these series here are non-stationary because it doesn't satisfy the condition of the mean. The mean here is going to be around this level, say, and the mean in here is going to be completely different. Okay, so this is a typical example of a non-stationary series. Now, how then a stationary series looks like? Okay, so this really looks more like an index. What I mean is SP 500, NASDAQ, etc. Got it? Prices. What a stationary series looks like, guys, is something like this, no? And here you can see clearly that if you take a couple of intervals, same size. Simply move them in time. You see, just take a look to the mean. For example, here, we're going to be okay with that. The means are going to be very similar to each other. Perhaps the variance is going to be similar to each other, etc. Got it? But this restriction here, that having the mean, the variance, the skewness, kurtosis, all the moments of the distribution exactly the same when we move in time, this is very tricky to get in real life. Right? And that's why we have a weak version of this strict stationarity. Now, what series do we have that look like this? Well, returns. You know, so this is a stationary process. And the stationary process we can find, and we're going to see that, for example, returns. Okay, so based on the assumption that we really cannot find this exact equality of all the moments, what we're going to do is we're going to define a weak stationarity. Okay, so what is a weak stationarity, guys? The conditions are basically three conditions. So we have, first of all, the expected value of the time series is equal to mu, it's a constant, mu. In second place, that the variance of the series is constant and exists. So this implies that it is smaller than infinite, so it exists and is constant. And the third assumption that is really important, guys, is that the covariance of yt minus j equals, let's call it, this is going to be my sign for covariance gamma of j. Okay, so what is the meaning of that? The meaning of that, guys, is that covariance, it is independent of time. It depends on the size of the interval. So here my interval observations is j. Okay, what only matters for me is the distance, this space from here to here, what matters in order to compare covariances. So this means the following. For example, if we take the covariance of yt with yt plus 10, this is going to be exactly the same as the covariance of yt plus 100, for example. Let's say 99. Yeah, 100 is okay. Let me delete this. And yt plus 110. You see, the distance is 10 between these observations, and the distance between these observations is also 10. Okay? So this is crucial. This is what means for stationarity, weakly stationarity. What matters is the interval size. Okay? It doesn't matter the time. Make sense? From this weak stationarity, guys, we can define another variable, another definition that we're going to be using quite a lot, and is what is called a white noise process. White noise process is a special case of the weakly stationary processes. It has the following characteristics. So the expected value of the time series is again a constant. The variance again exists and is equal to a constant. And what is interesting here is that the covariance of yt with yt plus s or plus j, I think we have been using, is always going to be 0 for all j different from 0. Okay, so this means simply that the series here have no correlation, or they don't covariate. Okay, the covariance is equal to 0. So this is what is called a white noise process. That is basically a subset of the weakly stationary processes. Make sense? And there is one more that we're going to be using, and it's called the Theorem white noise process. That is simply when the mean equals 0. Okay, all the other conditions stay the same. And third, Okay. So with these definitions, guys, I think we're going to be in good shape and we can move forward. Now, there is an additional thing that is called, we know that the covariances, the covariance of yt plus j is what we call gamma j. And we have the correlation. Well, let's define first of all, what is the covariance of yt. Remember that the covariance on the same variable is simply the variance, and the variance is going to be named as gamma 0. Right? So this is my variance. And what is interesting, guys, is that we can define the correlation, right? So, and the correlation, we call autocorrelation coefficient. The autocorrelation coefficient, guys, is going to be called tau j, and tau j is simply going to be gamma j over gamma 0. Now, if we draw, if we start changing j from 0, 1, 2, 3, 4, 5, etc., by changing j from 0 to the infinite, what we get is the autocorrelation function. We're going to work with this later. Okay, but the graphs that we're going to obtain, guys, this is one example, can be from here when it's 0, then it goes like that, then goes like that, etc. Okay, so this is one example of how an autocorrelation function is going to look like. Now, what we know now, let's talk a little about the autocorrelation, the autocorrelation function. We are going to be really interested about the autocorrelation function. And there is one property, guys, that we already know, is the following. You know what? Assume that yt is distributed as a normal distribution, okay? Has a normal distribution. Then if you take a look to tau, so by the way, this is called tau. Okay? If we observe tau, guys, if we know this one here, tau is also going to be distributed as a normal, but you can see this one here is a standardized value. It's like the z in the statistics. So we remember that the c has, the mean is going to be 0, and its standard deviation is going to be simply, standard error is going to be simply 1 over square root of t. Got it? So this here is really interesting, because from here, what I can do is I can build a confidence interval. So I can do a confidence interval for tau, for example. So what I can argue is that tau, the population tau, is going to belong to, so the mean is 0. So it's going to be 0 plus minus, if we do a 95% significance level, it's going to be 1.96, 1 over square root of tau. So if we want to see if there is autocorrelation present in your series, the first way of seeing this one here is simply create a confidence interval, 196, 95% significance level, a confidence level. And then you simply replace the values here, and then you can obtain basically your first way of seeing if we have a significant autocorrelation. Okay. However, guys, there are two techniques that are useful for detecting autocorrelation, and on one of them is what is called the hypothesis testing is going to be. So what I want to test is simply H0. There is autocorrelation. Okay. Let's call it. There is no autocorrelation of order m, right? So the test that we're going to use two tests. One is the box and Pierce. And the box and Pierce simply says the following. It says that Q is the name of the test. Is going to be simply T, sum of, let's call, yeah, K equals 1 to M of tau of K, okay? Tau square of K. So if you rewrite this one here is simply K equal 1 to M T tau K square root of T, sorry, K of T, all this is squared. And we can prove that this is indeed a chi-square with M degrees of freedom. Right? So my null hypothesis, guys, is going to be that there is no autocorrelation of order M. The test that I can use is the box Pierce or Q. You're going to see this in EViews. And I simply multiply T's number of observations and this summation here. And this is going to be distributed as a chi-square with M degrees of freedom. Now, the problem with the box Pierce is that it is not good, it's not robust in front of small samples. When we have small samples, we are going to use another one. When we have small samples, what we are going to be using is the Lung box. It's also Q. So Q or Lung box is going to be, in this case, T plus 2, sum of I equals 1, or K, we're using K equals 1 to M of tau square of K divided by T minus K, okay? So, and this also is going to be distributed as a chi-square with M degrees of freedom. But this one here, as I mentioned to you, is very robust to small samples, you know, and what is interesting, guys, is that if you introduce this T plus 2 in here, so if you take a look to what is this over this, you know, if T is very large, so I always say infinite, but it's a very large number. So this number here basically tends to be equal to 1. And if it's equal to 1 or very close to 1, what do we get at the end is simply T sum of tau square K. That is basically the box and Jenkins. Okay. Okay, so we know more or less how to detect the presence of autocorrelation. So we have the confidence interval, we have the box and Pierce, and we have the Lung box. So remember, Lung box is for small samples, and the Lung box equals the box Pierce, technically equal when there's a very large sample size. Okay. Now let's start working with specific time series models. Let me say this one, and let's start with a model that is extremely simple to understand, and it's called the moving averages. Or what is called also as MAQ model. Let me present the model first of all, and then we describe, and then we find the moments that we're interested, and then we're going to understand how to identify if we have an MA process. Okay, so let's define an MAQ process is going to be simply my series are equal to a constant, okay, mu, and then a series of errors. So this is U, so this is going to represent my errors at time t, plus theta 1 errors at time t minus 1. If I do this Q times theta Q ut minus Q. And what is interesting, guys, the assumption we're making is that U's are zero mean white noise processes. Okay, so this is my main assumption in this model. So I will write this a little. So I need to introduce a multiplier here. So let's define that LYT is simply YT minus 1. So basically this is L. So this power here is the one that determines the number of lags. So another example, L cube of YT is going to be, for example, YT minus 3, etc. Got it? So I will rewrite this equation number 1. And I will say this is equal to mu, and I will write ut. And I will write this one here as plus theta 1 L ut plus theta 2 L square ut plus, if we continue this one here, it's going to be theta q L to the q ut. Right? Of course, we have common factors ut. So yt is going to be equal to mu, there's a constant, plus 1 plus theta 1 L plus theta 2 L square plus theta q L to the q that multiplies ut. Okay? So what I call this part here, I will call this part here mu plus big theta, caps theta of ut. And this one here, guys, is a short notation of my MA process. So this writing here, okay, so this one here is caps theta, okay? So slash theta. Okay, so this is your MA model, guys. And as usual, what we're going to be doing is, okay, so I have an MA model. How do I detect this MA model? In order to detect an MA model, what I need to do is I need to know what are the properties of this time series, okay? Okay, so now, where's my share screen here? So what we're going to study now are the properties of the MA model, okay? And with these properties, you're going to understand how to detect MA processes, MAQ processes. Well, in order to understand this one here, let's do an example, okay? Let's do an example. Let me assume an MA2. Okay? It's not so simple, not so complex, just to allow me to show you how this works. So if it's an MA2, this is going to be equal to mu plus ut plus theta 1 ut minus 2. As usual, ut is a zero mean white noise process. Right? Now, what I will do is I will try to find the first moment. Let's find the expected value. Let's find the expected value of yt. So I simply introduce the expected expectation operator here. This is a constant, so this is going to be mu, expected value of ut plus theta 1 expected value of ut minus 2. By definition, guys, this is a zero mean white noise process, so these two get out, and so the mean of my R process is simply equal to the constant. So we have the first moment, then the expected value of the series is going to be equal to the constant. Just to make it easier, guys, okay, let's assume, just for simplicity, okay, let's assume that the constant equals here. So this implies that my MA process, MA2 process is simply going to be ut plus theta 1 ut minus 2. Okay, so now let's start talking about the second one. Let's talk about the variance of my series of yt. Okay, so the variance of my series, guys, remember, is simply expected value of yt minus expected value of yt, all this is squared. But if I'm assuming that mu that is equal to expected value equals 0, so this part disappears, and this is going to be simply equal to expected value of yt squared. Okay? So let's do this. What is expected value of yt squared? It's going to be equal to the expected value, okay, yt of yt. So it's going to be mu t plus theta 1 mu t minus 2. So this is yt times yt, ut plus theta 1 ut minus 2. Now, if I do the multiplication here, it's going to be ut squared plus theta 1 squared ut minus 2 squared. And then all the other terms are cross terms. You see, ut multiplied by ut minus 2. Sorry, this is ut minus, mistake here, my mistake. This is ut minus 1. So I want to do 2 components plus theta 2 ut minus 2. Okay, so this doesn't change. Theta 2 expected value, this is 1 of ut minus 2. This also disappears. What I need to change here is this part here. So allow me to delete this part here. Yeah, I was saying there is something missing there. Okay, so this is going to be ut minus 1 plus theta 2 ut minus 2. So this is yt. And this is 1 plus theta 2 ut minus 2. Let's be sure that you understand this. This is 1. Okay. Okay, so now times the same. Ut plus theta 1 ut minus 1 plus theta 2 ut minus 2. Okay. If I multiply, it's going to be mu t squared, sigma 1, theta 1 mu t minus 1 squared plus theta 2 mu t minus 2 squared plus cross terms. What I mean cross terms is simply that mu t goes with mu t minus 1, mu t minus 1 goes with mu t minus 2, etc. Then when I take the expected value of the cross terms, guys, remember we're talking about a white noise process, and the covariance of the white noise process of ut with ut minus j, when j is different from 0, is going to be 0. So basically, when I apply the expected value, the expectation operator to these ones here, these ones are going to disappear. Okay? And then what we get here is what is the expected value of mu t squared? So this can go this way, mu t squared plus theta 1 squared expected value, sorry, theta 1 squared expected value of mu t minus 1 squared plus theta 2 squared expected value of mu t minus 2 squared, okay, plus 0. All the other terms cancel out. What is the expected value of mu t squared? Remember, this is a white noise process, and we define this one here to be sigma squared. So it's a constant variance and it's less than infinite, so it exists, plus theta 1 squared sigma squared plus theta 2 squared sigma squared. So finally, guys, what is my variance? And remember, my variance is something that I call gamma 0. Gamma 0 is going to be simply this one, 1 plus theta 1 squared plus theta 2 squared. And here we go. So we got the second moment. My variance is going to be equal to this equation here. Moving to the covariances, okay? What I will do is I will try to find what is the covariance, what is gamma 1, basically, okay? So gamma 1 is simply the covariance of yt with yt minus 1. Okay, so this is going to be exactly the same as before. It's expected value yt, we said is going to be ut plus theta 1 ut minus 1 plus theta 2 ut minus 2. Okay, that multiplies this one lagged once. So it's ut minus 1 plus theta 1 ut minus 2, this one minus 2. And this one lagged one more, theta 2 ut minus 3, okay? Then the same, what we try to do is we try to do the factors that multiply each other so they are the same time. And all the other ones are going to be cross elements. So the only ones that we can multiply here correctly are mu t has no pair. Okay, so it's going to be cross term. This one here goes with this one here. So I have theta 1 mu t minus 1, this with this. Then I have plus, I have this one. So it's going to be theta 1, theta 2 mu t minus 2 squared. So this is also square. It's this one with this one, and this one with this one, okay? Plus cross terms. If I apply this one here, I will have, remember, expected value of the square is sigma. So it's going to be theta 1 sigma square plus theta 1 theta 2 sigma square plus 0. Okay? So this one here, guys, is my gamma 1. Let's find gamma 2. We are almost there to show you what are the properties of this time series. So now is the covariance of yt with yt minus 2. So I will copy basically the same, but now I need to lag yt twice or 2 periods back. So ut is the same, yt is the same. Theta 1 ut minus 1 plus theta 2 ut minus 2. And then I lag twice is ut minus 2 plus theta 1 ut minus 3 plus theta 2 ut minus 4, right? Again, I try to find the elements that are the same time period. This doesn't have a pair, this does not have a pair, and the only one that has a pair is this one here. This with this. So it's going to be theta 2 mu t minus 2 square plus the cross elements. And then finally, this one here is then what we call gamma 2 is going to be equal to theta 2 sigma square. And then it is obvious what is going to happen with gamma 3, guys. I will do this just to show you. But indeed what happens with gamma 3 is going to be is the covariance of yt minus 3 that is going to be equal to the expected value of ut plus theta 1 ut minus 1 plus theta 2 ut minus 2. That multiplies, I need to lag this 3 times. It's going to be ut minus 3 plus theta 1 ut minus 4 plus theta 2 ut minus 5. As you can see, guys, if we multiply these ones here, I will have the expectations of purely cross products. You agree? And the expectations of cross products equal 0. Okay, then generalizing this one here, guys, what we can argue is that gamma j is going to be 0 for all j larger than q. You see, q was, in my case, this is an MA2. So this is q. This implies that for the covariances larger than 3 or larger than 2, sorry, larger than 2 are going to be all equal to 0. Okay? And that's going to be the way we're going to identify, or we're going to identify the MA processes. Now, let's do something more related to this one here. Remember, these are the autocovariances. Now let's define the autocorrelations, okay? So what is my autocorrelation of order 0 is simply gamma 0 over gamma 0. So this is going to be always equal to 1. Okay, so the first autocorrelation or correlation of order 0 is going to be 1. Now what happens if I have the autocorrelation of order 1? It's going to be simply gamma 1 divided by gamma 0. So if we remember, gamma 1 was equal to sigma square theta 1, theta 1, theta 2. And then we divide this one by sigma square 1 plus theta 1 square plus theta 2 square. So we simplify these ones here. And then theta 1 is going to be equal to theta 1 plus theta 1, theta 2 divided by 1 plus theta 1 square plus theta 2 square. So this is my second autocorrelation. Sorry, not my second, autocorrelation of order 1. Now, let's continue moving with autocorrelation of order 2. is going to be gamma 2 over gamma 0. So this is going to be sigma square theta 2 divided by 1 plus theta 1 square plus theta 2 square multiplies sigma square. So they to cancel out. So theta 2 is going to be equal to tau 2 is going to be equal to theta 2 1 plus theta 1 square plus theta 2 square. And of course, as soon as the autocovariances of order 3 and above are 0, so what we can argue is that tau 3 is going to be equal to 0, you know, for, let's do the generic, this is J, for all J greater than 2, okay? So with that, we have our complete set of characteristics. And so let's do one example. I prepare one example here just to show you how this looks like. So let's do one example. Let's assume, guys, that we have theta 1 equals minus 0.5 and theta 2 equals 0.25. And what we want is to draw let's draw the autocorrelation function that is also known as ACF, autocorrelation function, okay? Then let's do that. So T0 is going to be, of course, 1. T1, if we simply replace the values, is going to be minus 0.5 plus minus 0.5 that multiplies 0.25 divided by 1 plus 0.5 squared. Remember, it's minus 0.5, but better if I do this, plus 0.25 squared. Then, guys, if you solve this one here, you should obtain more or less minus 0.476. And tau 2 is going to be equal to this formula here. It's going to be 0.25 divided by 1 plus minus 0.5 squared plus 0.25 squared. And so this is equal to 0.190. Right? So how the autocorrelation function looks like for the MA process. So I have 1, 2, 3, 1, 2, 3, and 0. When it's 0 is 1. So let me draw perhaps this one here. So we have a bar here. When it's 1 equals 0.47 negative, so we have around here. And when it's 2 equals 0.19, perhaps around here. And after that, it goes to 0, right? So what we can see is perhaps a graph like that. So we're going to see this in Nebius or Arp. And then after that, this is a series of 0, right? So just taking a look to the ACF for the MA process, guys, we can identify that. If we see a process that has, you know, a couple of autocorrelations different from 0, and then after that is 0, but we can argue, oh, you know what, this is an MA2 process. Or if we have 3 or 4 bars different from, significantly different from 0, we can say, you know what, it's an MA3 or an MA4 respectively, right? So this is the MA process. It's the most simple process we're going to be seeing, but it is very useful for modeling purposes. And now let's move to another model that is called the autoregressive model. And we call this ARP, okay? What is how the ARP looks like? Well, the ARP model looks like this, guys. YT equals, okay, let's do a constant, plus psi 1 YT minus 1, plus psi 2 YT minus 2, plus psi P YT minus P, plus an error. And this one here again is a zero mean white noise process. Okay, so I will do the same as I did for the MA process. What I will do is I will move all the YTs to the other side. So this is YT minus psi YT minus 1 minus psi 2 YT minus 2 minus psi P YT minus P equals the constant plus the error. Okay, so if I apply the operator here, there's going to be psi 1L YT minus psi 2L squared YT minus psi P L to the power P YT, and this equals mu plus UT. Okay, so a common factor YT. So it's going to be 1 minus psi 1L minus psi 2L squared minus psi P L to the power P of YT. And this is equal to mu plus UT. So in general terms, guys, this is caps phi of L, that is this part here, times YT equals mu plus UT. So this model here is my R-type model, RP model. Now, one thing that we need to understand when we talk about the ARP models is something that is called stationarity. Okay, the stationarity condition of ARP models. And in order to understand this one, is stationary. Okay, so what is the stationarity condition of the AR process? Let's understand the following. Let's assume that I have the following very simple AR1 model. Okay, so I have YT equals YT minus 1. Let's do the complete model first, and then I will delete something. Mu plus psi 1 YT minus 1 plus UT. Okay, so this is my zero mean white noise process, and let's make some assumptions here. Let's assume for now this is 0. This is a zero mean white noise process. Okay, and let's assume the following. Let's assume that YT minus 1 equals 0, and let's assume that there is a shock. UT at time t, and the shock is equal to 0.5. Got it? Now, what happens with my series under the following assumptions? Let's assume that psi 1 equals 1.5, for example. Then my model is going to be YT. Okay, I'm assuming mu is 0. Let's assume also, just to make it simpler, mu 0. So this mu 0 plus 1.5 YT minus 1 plus UT. If I replace with the values, here is 1.5 times 0 plus 0.5. So basically this is equal to 0.5, right? So now what happens at period number 2? At period number 1. YT plus 1 is going to be equal to 1.5 YT minus 1. So it's going to be YT plus 1 minus 1 is YT. UT disappears because the shock appears only in one period. So this is going to be equal to 0.5 times, 1.5. This is going to be equal to 1.5 that multiplies 0.5. YT is 0.5. So this is equal to, let me use my calculator here. This is going to be equal to 0.75. So what is the value of YT plus 2? Guys, sorry, I need to be stopping from time to time this recording because there's some work going on in my home. So sorry for that. So, okay, so this is YT plus 2 is going to be 1.5 of YT plus 2 minus 1, YT minus 1. So this is going to be 1.5 times 0.75. And this is equal to 1.125. What is interesting here, guys, is that when this number here is larger than 1, this process never goes back to 0. That is the mean. So that's why this process is called a non-stationary process. It explodes. If you continue doing this experiment, guys, you can see that this goes up to the infinite. Non-stationary process. And this is something that we don't observe a lot in using financial data. Normally we have a shock, we go up or down, and then we go back gradually to the mean. Right? So this is what is called mean reversion. Oh, by the way, yes, in finance, guys, this is called the mean reversion property. Okay, it's the same. Stationarity condition is mean reversion. Now, what happens if I have psi 1 equals 1? Okay, so I'm changing now only psi. So my model is going to be yt equals 1 times yt minus 1 plus ut. So it's going to be 1 times 0 plus 0.5. So this is equal to 0.5. So at period 1, the shock is 0.5. But observe what happens in the next period. This is going to be 1 times yt is going to be 0.5. What happens at y plus 2? It's going to be y times t plus 1 is equal to 0.5, etc. So what happens here, guys, is that once you shock the system stays there forever. So they never go back again to the mean. Okay. So this process here is also a non-stationary process. It's called the random walk process or unit root process. Okay, so these three names are the same. And finally, guys, what happens, for example, if psi 1 equals 0.5, less than 1? You can realize the same. Let's do the same example. This is going to be equal to 0.5 yt minus 1 plus 0 plus ut. This is going to be 0.5 times 0 plus 0.5. So my shock initially is equal to 0.5. Then I go yt plus 1 equals 0.5 of yt. So this is 0.5 of 0.5. This is 0.25. Now we go to yt plus 2 is going to be equal to 0.5 of yt plus 1. So this is going to be 0.5 of 0.25. So this is 0.125, etc. You can see, guys, that this process here, okay, so we were at 0, we moved, and then we smoothly go back to the mean. This one here, we moved, and then we stay there. And this one here, we moved, continue moving exponentially, right? So this is an stationary process. This is a process that has a mean reversion. And these are the processes we're going to be interested the most in this class. Okay, so in general, how do I define the stationarity condition? The stationarity condition, guys, comes from this equation. Let's continue working with this and then we can generalize. So if I have my AR1, okay, so my AR1 is equal to this plus psi 1 yt minus 1 plus ut. So if I write this one here in the other side, yt minus psi 1 yt minus 1 equals mu plus ut. If I do the same math as before, you can show, guys, that this is equal to 1 minus psi 1L and mu plus ut. The condition, guys, for stationarity is going to be, remember that this one here, I wrote this one here in general. The condition is based on this one here, right? And the conditions are the following. The roots, that all the roots, the condition is that all the roots of the characteristic equation of caps psi fall outside the unit circle. So it basically means that the values are larger than 1 absolute value, okay? values are larger than 1 in absolute value. So now let's understand what is this characteristic root and characteristic equation and roots. So let's assume this example here. So let's call this one here. From 1, the characteristic equation of this one here is going to be simply 1 minus psi 1, I replace by z, and then I equal this to 0. And then I'm simply, what are the roots? Are simply all the values of c that satisfy this equation. All right? So from this R1, it's very simple. C is going to be equal to 1 over psi equal to 1. So what is the stationarity condition? The stationarity condition is that the absolute value of c must be larger than 1. So this implies that the absolute value of 1 psi 1 should be larger than 1. What is interesting, guys, is that this condition here is exactly the same as requiring that the coefficient here, the absolute value of psi, is smaller, strictly smaller than 1. So this is the main stationarity condition that we're going to be working with. Okay, and stationarity condition is crucial for having a solution linked to the Erp process. Let's do one example. It's the following process, a stationary process. Or a stationary process. So let me give you this example. Yt equals 3yt minus 1 plus 2.75 L squared, sorry. Let me do this part here. I'm just going directly to Yt minus 3L Yt plus 2.75 L squared Yt minus 0.75 L cubed Yt equals, let's say, Ut, the error, right? So my characteristic equation here is going to be 1 minus 3c minus, sorry, plus 2.75 c squared minus 0.75 c cubed and equals to 0. Okay, so if we do some factoring here, we can arrive to, 1c. Don't stress about that. We're going to use the program to compute this for us. Minus 1.5 c1 minus 0.5 z equals 0. So from here, c equals 1. Here, c equals 2/3. And from here, c equals 2. All right, so what is my condition here, guys, is that all my roots are larger than 1. Okay, this does not satisfy that, this does not satisfy that, this is the only one that satisfies this one here. Right? And as soon as I have only one process, even I have only one of the roots are larger than 1, but the other ones are smaller than 1. Okay, so this implies that the process is non-stationary process. Okay. Remember, my requirement is strictly larger than 1. You see that it's not larger or equal, it's larger than 1. So, and the only one that satisfies this rule is this one here, but I have two roots that are not there. So it's not all. So this implies that this process is a non-stationary process. Right? Okay, so give me 1 second. Okay, so let's continue and let's start working now with the properties of the Erp processes. Okay, like we did with the MA process. Now we're going to talk about, its properties of the Erp process. Okay, the same process. So now let's start talking. First of all, let's start working with Erp1. My Erp1 is going to be Yt equals mu plus psi 1 Yt minus 1 plus Ut. And Ut is my zero mean white noise process. Okay, so here what we're going to be using, guys, is the wall decomposition theorem. Wald, this is an O, Wald's decomposition theorem. That basically says, guys, that an Erp process can be decomposed into two pieces. One deterministic piece, that is basically my constant, and one MA process. And the order of this MA is going to be an MA infinite. Okay, so let's understand how this works. Let's take a look to the following, guys. So YT minus psi1, YT minus 1 equals mu plus UT. Okay, so from here, I know that this is going to be YT minus psi1 L YT equals mu plus UT. So from here, YT that multiplies 1 minus psi1 L equals mu plus UT, correct? And then if I move this one here, I will move this one, yes, I will move this in the other side. So and let's assume again, just to make it simpler, that mu is 0. Okay, so this is going to be equal to UT 1 minus psi1 L. What is interesting, guys, is that this one here is a geometric progression. This one here is exactly the same as having 1 plus psi1 L plus psi1 L squared plus infinite of mu t. So if you see, this one here is going to be equal to UT plus psi1 UT minus 1 plus psi1 UT minus 2 plus to the infinite. So what model is this one here? As soon as it depends only on the lags of the errors, this is an MA. And what is Q? Infinite. Okay? And what is my constant? Well, my constant is here, is mu. Okay. Now let's start understanding this one here. But what is interesting about the Wald decomposition theorem is that we have two components. The mu, that is a constant, the deterministic part, and MA infinite. And as soon as we know already how to find the MA values, how to find the characteristics of the MA, it's going to be extremely simple to work with this. Okay? Now, so let's continue. Let's start working and let's find out the moments. First of all, let's find what is my expected value of YT. Okay, so let's do that. I know that YT equals mu plus psi1 YT minus 1 plus UT. Now I will develop this one here. This is equal to mu plus psi1. I know that if I know a YT, I can know YT minus 1 is going to be the constant plus psi1 YT minus 2 plus UT minus 1. Okay, so if I simply agglomerate some values, it's going to be mu 1 plus psi1 plus psi1 square YT minus 2 plus psi1 UT minus 1. Okay, and what is interesting is what I will do is I will apply here the expected value. So if I apply the expected value, this one here is a constant. So this is mu 1 plus psi1 plus this one here is square expected value of YT minus 2 plus psi1 expected value of mu t minus 1. And you can see here that as soon as the errors are zero mean white noise processes, all the errors are going to disappear. So what I will focus is only on the YTs. So I continue working with this. It's going to be mu, this one here, plus this one here, okay? And then here I have the expected value of mu, plus, and I will forget about the errors because they don't intervene, plus psi1 YT minus 3. So this is going to be, I have this times this, so I have mu 1 plus psi1 plus psi1 squared plus psi1 cubed expected value of YT minus 3. And if I do this infinite times, you know, I do this infinite times, what I will get is this 1 plus psi1 plus psi1 squared plus this goes to the infinite plus psi 1 to the infinite power, let's say, of gamma 0, of a y0, the first observation that you have from your series. Now, if we have a stationary process, so this implies that the absolute value of this one here is smaller than 1. So what happens with a number that is smaller than 1 to the power infinite? This part simply goes to 0. This part disappears. So what is my expected value then? My expected value is going to be all this part here. Okay, and this is a geometric progression also. So finally, this one here, my expected value is going to be simply mu. So this is mu, it's not u, it's mu, it's my constant. Mu over 1 minus psi 1. So this is going to be my expected value of my R1 process. Okay. Let me now, just as usual, to make it easier, let's assume let me assume that let me assume that mu equals 0. Okay, just to make it our R process much simpler. So this implies that yt is going to be equal to psi 1 yt minus 1 plus ut, right? So what is the same as yt 1 minus psi L equals ut? And as I told you, this is going to be simply yt equals ut 1 minus psi L. And this one here is going to be equal to 1 plus psi 1 L plus psi 1 L squared plus infinite ut, right? So this is going to be my transform variables. Sorry, this is square, L squared, etc. Now, once I know this one, I can do, this is an MA process. Okay? So we have been, in the previous couple of minutes ago, we have done the process of how to find the properties of an MA process. So we are going to do the same technique now. So let me find the variance gamma 0. Okay, so gamma 0 is what, guys, is simply the expected value of yt squared. And if I do that, it's simply the expected value of, I will just put this here. It's going to be ut, this is yt, ut plus psi 1 ut minus 1 plus psi 1 squared mu t minus 2 plus psi 1 cube ut minus 3 plus this goes to the infinite. That multiplies the same. Okay, so it's going to be ut plus psi 1 ut minus 1 plus psi 1 squared ut minus 2 plus psi 1 cube ut minus 3 squared, not square, etc. As usual, what we try to do is we try to find elements that multiply, that times are the same. So this is going to be expected value of ut squared plus psi 1 squared ut minus 1 squared plus psi 1 power 4, this one with this one, ut minus 2 squared plus psi 1 power 6 ut minus 3 plus etc. plus all the cross terms. Okay. Now, when I apply the expected value to the cross terms, they disappear. And when I apply the expected operator to the square of the errors, this is sigma squared. So this is going to be sigma squared plus psi 1 squared sigma squared plus psi 1 fourth power sigma squared plus psi 1 6 sigma squared plus this goes infinite. So if I simply common factor sigma squared 1 plus psi 1 squared plus psi 1 fourth plus psi 1 6 plus this goes to the infinite. and this is geometric progression, so geometric series. So this is going to be equal to sigma square 1 minus psi 1. So this is your gammas here. Okay. It's very simple, but it takes a little time, but it is very simple. Let's do now gamma 1. So gamma 1 is simply the expected value of yt with yt minus 1. And this one here is going to be equal to the expected value of, I copy the first one, ut plus psi 1 ut minus 1 plus psi 1 squared ut minus 2 plus psi 1 cubed ut minus 3 plus this continues. Now I lack this one period, ut minus 1 plus psi 1 ut minus 1, not 1, minus 2, plus c squared ut minus 3 plus psi 1 cubed ut minus 4 plus this continues to the infinite. Right? So now what are my elements that have equal? This one disappears, equal time disappears. So now I have expected value of psi 1, this one, with this one, psi 1 mu t minus 1 squared plus psi 1, this one, with this one, psi 1 cube mu squared t minus 2 plus psi, this one with this one, psi 1 5 mu squared t minus 3 plus cross terms. Okay, then if I apply this one here, I have common factor is going to be psi 1 sigma squared, 1 plus psi 1 squared plus psi 1 fourth plus psi 1 6 plus, that's it. Then if I simply reorganize this one here, gamma 1 is going to be equal to psi 1 sigma squared over 1 minus psi 1. Okay, so I have the first two, the first covariance. Let's find the second covariance. And I think that with that we can generalize. If I want to do the second covariance, that is simply equal to the expected value of yt with yt minus 2. And this is going to be equal to the expected value of ut, where's my, yeah, plus psi 1 ut minus 1 plus psi 1 square ut minus 2 plus psi 1 ut minus 3. This is cube. Plus this continues to the infinite, and then I need to log this twice. It's ut minus 2 plus psi 1 ut minus 3. Oh, no, this is to the power 1. Plus psi 1 squared mu t minus 4 plus psi 1 cube mu t minus 5 plus etc. And so this one disappears. There is no pair here. This one here also disappears. There is no pair here. So this one here is going to be equal to this one with this one is psi 1 squared mu t minus 3 squared plus this one with this one. This is sorry, I'm this with this. It's not this one here. It's this one here with this one here. Now let's do this one here with this one here. So it's going to be, delete this one here. No confusion here. This is 1. This is phi 1. Yeah. So this is this is psi 1 power 4 mu t minus 4 squared, and then you continue to the infinite. So this is going to be equal, this is squared, so it's going to be common factor is going to be this one. So multiplies 1 plus phi 1 squared plus phi 1 power 4 plus etc. And then from here, guys, you obtain this one here is equal to then if we continue doing this exercise, now we continue gamma 3, gamma 4, you can see that this one here is going to be equal to psi 1 cubed sigma square 1 minus psi 1. Gamma 4 is going to be psi 1 fourth power sigma square 1 minus psi 1, etc. Right? Good. So now, as we did before, let's talk about the autocorrelation function, the ACF of an MA process. Oh, sorry, of an ARP process. Tau 0 is gamma 0 over gamma 0, so this is going to be equal to 1. Tau 1 is going to be gamma 1 over gamma 0. So gamma 1, where's my gamma 1? What was gamma 1? Oh yeah, it's going to be psi 1 sigma square 1 minus psi 1. And what is gamma 0 is sigma square over 1 minus psi 1. So at the end, I obtain gamma 1. So tau 1 equals gamma 1. I will do this in here, okay? I will continue in here. What is tau 2? Tau 2 is going to be gamma 2 over gamma 0. Gamma 2 is going to be psi 1 square sigma square over 1 minus psi 1 over sigma square 1 minus psi 1. So if you simplify this one, this goes equal to psi 1 square. And then from here, you can see the sequence. Psi 3 is going to be psi 1 cubed. Tau 4 is going to be psi 1 power 4, etc. Right? Now, how the autocorrelation function looks like? Well, the autocorrelation function in an R process, guys, is going to be, let's do 1 first. No, it can be in general, it can be like that. It's going to be 1. And then it's going to, if it's in a stationary process, it's going to be decreasing towards 0. But this goes to the infinite. You agree? So technically, the smallest psi, the faster you go back to the 0. The closer to 1 is going to basically mean that your red bars are going to be very, very persistent in time. And if it's larger than 1, your red bars are going to go from 1 going up, going up, going up, going up, going up. Right? So this is the way that you can check for an R process. Of course, you can find other R processes that have a mixture of bars. So you can have bars up, bars down, bars up, down, etc. So this is the way that you can identify the R processes. Got it? I think that we stop here. Hopefully you can review this material here before the class. This is our first class of a Univariate time series. It is important you understand this part here. I will do a 5-minute review in the class that corresponds to this time series. And I will try to prepare more material for you so you can be reading and discussing and preparing for the class. Okay, guys, a pleasure and talk soon. Bye-bye.